Hi everyone, this is Mr. Ruhoy, and this is an Algebra 2 video for graphing trigonometric functions. In this video, I'm going to go through three examples of sine and cosine waves that have transformations being applied to them. So we're going to talk about amplitude, we're going to talk about period, and then we're also going to look at vertical and horizontal shifts, shifting it left or right or up or down. And those are going to be what we call phase shift and displacement. But before we start with any of those, the important thing I need to talk about now is the key points that make up every sine wave and every cosine wave. So these four pictures here show the 5 key points that make up a sine wave, a cosine wave, and I also have the reflections, a negative sine and negative cosine. Because if you want to graph a sine or cosine wave, all you need to use are 5 points. And those 5 points would be a min, a max, in the case of a cosine, multiple maxes, and then x-intercepts. Your job is to remember what the basic shapes of these trig functions look like, so that when you're applying transformations to it, all you have to do is think back to what these basic shapes look like and figure out where the min and max points and the scaling needs to be, and how it's going to appear in your graph. So I'm going to refer back to this page throughout the video. Well, let's take a look at our first example. I want to graph one cycle of y equals negative 1/2 the sine of 1/2 x. So you can already see that this thing is negative. It's being reflected. So our graph is going to look like a negative sine wave. It's going to look like this. So that's what our end result is going to look like. Our job is just to figure out how to label the x and y axis. So the first thing I just like to start with is figuring out the amplitude, value of b, the period. The amplitude is going to be a positive 1/2. And I know there's a negative 1/2 in front of the sine wave, but the amplitude's always a positive number because the amplitude is just a distance. It's a distance between your midline, which is your central axis, the horizontal line that cuts your wave in half. It's the distance between that midline and your maximum. And it's also the same distance from that midline to the minimum. So it's always just a positive number. It's a positive distance. And that is really coming from the vertical stretch, or in this case, vertical shrink. Then we have the value b. That's the number of cycles you have from 0 to 2 pi. This tells us that if we were to graph the sine wave from 0 to 2 pi, we would only be drawing half the sine wave. The period tells us how long it takes to graph one full cycle. And that's what our directions say we have to do. We have to graph one full cycle. So in this case, we're going to start at 0 because there's no shift there's no left or right shift. So if we start at 0, that means that we're going to end at 4 pi because that's the distance, that's how long it would take to graph one full complete cycle. So now that we have that, I have an xy axis here that I started to label. And in the blue, that's where I have, I show this thing going up to 1 and down to -1. But our amplitude's 1/2, so the highest this point's going to go to is 1/2, and the lowest it's going to go down to is -1/2. I just include the 1 and -1 just for scaling and reference. But here, I have the scaling for the x-axis. That part's very important because that's how we're going to label our x-axis, and that's going to show how far each of those 5 key points are spaced out from each other. And the way you figure out that scaling is doing the period times 1/4. And the reason we multiply 1/4, we always multiply 1/4 for the scaling, because if there are 5 points in the sine wave, that means that it's being split up into 4 different sections. Every sine wave, every cosine wave can be split into 4 different sections. Because, very simply, all those points come from the unit circle, which has 4 quadrants. So that's why every sine wave has 4 different sections. So the period's 4 pi. We're going to multiply 1/4, so that gives us pi. And that's why each of these points are separated out by a distance of pi. So I start at 0, and I add pi. I add another pi that gives me 2 pi. I add another pi to 3 pi, and then 4 pi. So that's the distance between each of those little tick marks. So finally, we can just begin drawing in the points. As a reminder, the one I have circled here in purple, that's going to be that's what this is going to look like. It's a reflected sine wave. So we're going to start at 0, 0 right here, and then our function goes down. It goes back up, goes up to our max, and back down. And it looks roughly something like that. And that's it. So let's take a look at our next one. So I want to graph one cycle of y equals 2 cosine of 3x plus 1. So some initial analysis, we can see the amplitude is a positive 2. And then our value of b is 3. That's the number of cycles we have from 0 to 2 pi. So if we were to graph this thing from 0 to 2 pi, you would actually see 3 full cycles. But all we need to do is graph one cycle. So if we want to graph one cycle, we're going to start at 0, and we're going to end at 2 pi over 3. Because that's how long this graph needs to go in order for us to graph just one cycle. That's all we need to graph. If we were to draw this thing to 2 pi, there'd be 3 cycles, but we don't need that many. We don't need to draw that many points. Now let's talk about our shifts. As I mentioned in the beginning of the video, phase shift is your horizontal shift. That's the left and right. But we don't need to graph that for this one. So if we have, so there's no phase shift, there's no left or right. In the next example, you'll see what that would look like. So we'll just put that on hold for now. But this graph does have some displacement. There is a vertical shift that's moving the graph up or down. And we get that from this value right here. If you're adding a number at the end of the function, if you're adding something to the entire sine or cosine wave, that's your displacement. That's your shift up or down. In this case, we're shifting this cosine wave up positive 1. Now this is where it gets a little tricky. The displacement tells us the location of our midline. That's the central axis, that horizontal line that cuts this wave in half. So our midline is 1. And I'm going to show you when we graph it, I'm going to show you where that's located. The max, the highest this point's going to go to is not 2. I know the amplitude's 2, but if it wasn't being shifted, the amplitude would set the maximum point at 2. But because we're shifting this function up another unit, that means our maximum is going to be at 3. And you can calculate that by doing the midline plus the amplitude. 1 plus 2 is 3. The minimum, the lowest point, if there was no displacement, it would be negative 2. However, we're shifting this cosine wave up 1 unit. So that would place our minimum at negative 1. Or you could just calculate midline minus the amp. 1 minus 2 is negative 1. So that's all the initial information we need to do. So let's start graphing this thing. We saw that the maximum is 3, and then the minimum is negative 1. So I just labeled in blue, I just labeled the y-axis from 3 to negative 3. I thought that was fair. And now, in order to figure out, let me get rid of that. In order to figure out the scaling, we're going to do the period times 1/4. We're always multiplying 1/4 because every cycle can be split into 4 sections. So we would do the period 2 pi over 3 times 1/4. That would give us 2 pi over 12, and you can simplify that to pi over 6. So that when I wrote out the scaling on the x-axis, I labeled it as 0, pi over 6, and now I'm just going to add pi over 6 each time. You get 2 pi over 6, 3 pi over 6, 4 pi over 6. And now you don't have to reduce that if you don't want to. You really should, but it's easier to see it when it's not simplified because you can see that you're really just adding to the numerator 1 pi each time. You go from 0 to 1 pi over 6, 2 pi over 6, 3 pi over 6. It's a lot easier to kind of see it this way if you don't simplify it. So it's okay if you leave it that way. In the end, if you want to simplify, because you certainly can simplify most of those, that would be fine. All right, now this is the good stuff. So let's draw our midline here. I'm going to use a dotted line for it. I'll do it in red. So the midline is 1. So this is the horizontal line that cuts this wave in half. You don't have to draw a dotted line, but I always kind of suggest it. I think it helps a little bit. And now our maximum is at 3, and our minimum is at -1. All the x-intercepts are going to be not on the axis, but they're going to be on the midline. So let's just take a look. This is a regular cosine function. So that means that our function is going to look like this guy. And it's going to start at our maximum point, because cosine waves always start at the max. So our first point is going to be where our max is located at, which is going to be 3. That's our first point, right at 3. Do this, that doesn't look... That's okay. All right, so the next point that we have for a cosine wave is that it hits our x-intercepts. But we're not going to be on the x-axis because this thing is being shifted up. Instead, our next point is going to be on the midline. The next point that we have for a cosine wave is our minimum. And the minimum for this one is -1. Next, we have an x-intercept, but it's not really an x-intercept. It's a point on our midline. And then we have a max. A cosine wave always starts and ends at a max point. And if we connect it, there it is. So you can see the midline here. Because we shifted this function up 1 unit, everything got shifted up 1. Instead of the maximum being at 2, it got shifted up to 3. Instead of the midline being at -2, it got shifted up to -1. And the points that were the x-intercepts are now located all at 1 on our midline. And one thing I just want to point out really quick, the distance between the midline and our max is 2. The distance between our midline and the minimum is also 2. And that's the definition of the amplitude. So for example 3, we're going to graph one cycle of y equals the sine of x plus pi over 4 plus 3. So we have our amplitude being 1. We have our value of b. That's, again, that's the number of cycles we have from 0 to 2 pi. And we figure that out by looking at what number is being multiplied, what constant is being multiplied to our variable x. In this case, nothing, so there's nothing being multiplied to x, so it's just 1. And the period is then going to be 2 pi over the value of b, which is 1, so we get just 2 pi. And again, the period is the distance you would have to graph one full cycle, the length of one full cycle. Now, this one gets interesting. We have a phase shift. The phase shift is the horizontal shift, the left or right shift. And if you remember your rules for transformations, when you have a horizontal shift, it's always opposite of the sign that's in the equation. So in this problem, we're inside the parentheses, we're adding pi over 4. That means that we're shifting this to the left, in the direction of negative pi over 4. So horizontal shifts, the shift inside the parentheses is always opposite. So if we're adding pi over 4, that means we're subtracting pi over 4, and we're going to the left. And you could instead, for the phase shift right, we're going to the left pi over 4. But I intentionally wrote it as negative pi over 4 because I think that's going to help us with the graph. And the displacement, we also have a displacement for this one. That's positive 3. So our displacement is positive 3, which tells us that the midline is 3. The displacement tells us the location of the midline, how far this thing is being shifted vertically. So because the amplitude is 1, the maximum is the midline plus our amplitude, 1, which gives us 4. And the minimum is going to be the midline, which is 3, minus the amplitude, 1. So then 3 minus 1 gives us 2. Now, Since we have a max of 4 and a minimum of 2, I wanted to have at least a graph that goes at least to 5. So I just drew this from -5 to 5. And now the phase shift. Because if you notice, I didn't start this thing at 0. I actually started this thing to the left of the y-axis. I started this at -pi/4. That's because the phase shift tells us where to start our x-axis, where we should start this. Because if you think back to the other examples, we always just started it at 0. That was because for those examples, there wasn't any phase shift. We weren't shifting this thing left or right. But now we are. Now we're shifting this thing to the left, pi/4. So we're going to start our graph at -pi/4 to the left. The scaling from there is still the same. We're just going to do the period times 1/4. So we end up with a scale of 2pi/4. And if you look at the graph of what I labeled in red, we start at -pi/4 because of the phase shift. And then to get to our next little tick mark, we jump a distance of 2pi/4. So we have -pi/4 plus the scale of 2pi/4. That means our next key point is going to be located at +pi/4. The next one, we're going to add our scale of 2pi/4. So the next one is at 3pi/4. We jump another 2 to 5pi/4 and jump another to 7pi/4. And I just want to point out the total distance from -pi/4 to 7pi/4, that's a total distance of 8pi/4, which simplifies to 2pi, which is what we said our period is up there in the top right. So now that we have it labeled, now this is the easy part. We can just draw our function. This is a sine wave. So it's going to look like our sine wave here, where we're going to start at our central axis. We're going to start at the midline, which I'm going to fill in right now. The midline is at 3. I'm going to draw that in. And our function is going to start at that midline. So at -pi/4, have our first point. Then at pi/4, we're going to go up to our maximum, 4. Go back down to the midline. We're going to go down to our minimum, which is 2. And then back here. And if I were to connect this, there's our graph. And that's about it. All right, thanks for watching, everyone.